I would like you to consider a summation of a function and all its derivatives, as shown. What can you do with such a sum? Well, let's name it. Let's call it the power function. You can evaluate this at other functions to find a sort of transformation, if you'd like to say. However, the main topic I want to cover is what happens when you let this be a function itself, and namely, how it interacts with derivatives. Notice as we take y prime here, it's seemingly a duplicate copy of the initial function, just missing a term. But the magic happens when we subtract. That's a differential equation. To make sure that our formula works, we will try a couple examples. How about x? Well, by our formula, it's x plus 1. And well, yep, that works. We'll try another example. Y minus y prime is x squared. And according to our formula, once again, it works. So now the question is, how do we expand this? Consider a more powerful equation. Ky minus y prime equals f. Notice how our original idea doesn't work anymore. But what if we tweaked it a little bit? How about we just add constants in front of each of the functional terms? Well, let's try it. In order to solve, we'll have the same process. We'll multiply by k. Find the derivative of y. And simply subtract. And with a little bit of pattern matching, we'll be able to figure out our constants to get the equation that we want. In order to do this, we'll take this term by term. Notice, the f's cancel out, so our first term has to be 1 over k. Now comparing the second term, their difference must be 0, so that means that a1 is a0 over k. And in fact, in general, we can solve for an plus 1, which is simply an over k. This will give us the formula that we need. After solving for the constants through pattern matching, we're able to derive a general formula for this differential equation. How about we try an example? 2y minus y prime is equal to x. Y is 1/2 x plus 1/4 by our formula, and y prime is 1/2. After plugging this into our original differential equation, we will see yes, this actually works. Another note is that this can be more generalized to ay minus by prime is equal to f, where we simply just divide the b as long as it's not 0 because these are constants. Believe it or not, this idea can even be expanded upon more, with higher order differential equations. Simply repeat the same process with our constants and the process of elimination, and you will get an x that actually solves your differential equation. Before I go, I want to state a couple of things. Notice how this process of finding the solution seems to only work when a and b are constants. Also, this is not an end-all be-all solution. Notice if we have this equation and we use our method, this would actually diverge and blow up towards infinity. And the big question here is, what does all this mean? Because technically these equations are all self-referencing what they're solving for. So does this mean they have some special property? Navier-Stokes equations being solved? Who knows? So yeah, thank you to everybody for watching. I hope to make many more videos in the future.